Okay, folks, we are back. We are now back on the regular slides under Roman numeral 2, transition metals and coordination compounds. Before you watch this, there's a link, and I'll probably put this on your weekly assignments too. There's a link on the slides for a demo, which I did in the labs at SHIP. It's kind of cool, and it gives you sort of an informal overview of how this works. It's kind of interesting, watching some interesting color changes. That's something else I'll try to do. But I just want to go through the definitions here, and quite frankly, the battery is on the downswing, so I'm going to kind of get moving here on the definitions. You'll also want that chapter 19 handout when we get going from D2L. Okay, so let's get the basic definitions. I'm just going to kind of crank through this. All right, so hemoglobin was an example of a coordination compound. You have a transition metal, usually an ion, not always an ion. There's a couple that are just the metals, which are really weird. And they sit at the middle. They're also called metal complexes. Okay, so you have a central metal, cation typically, and you have covalent bonds with these things that grab onto them. And the word for that is a ligand. It's a really good word. Okay, and they come in and it's all the electrons come from the ligand to form the bonds, which is kind of unusual. Usually it's an electron here, and that's where we get the covalent bond. In this case, it's not. The ligands are the ones that are typically donating all of the electrons. So, some examples. Let's see, so what was that? That was number 1. It's the definition of a coordination compound. So, and we can talk about how these form as a chemical reaction. So let's just do, and usually we're talking about aqueous solution. So we dissolve some iron, compound that has iron plus 2. And this is a pretty common one, is the cyanide anion. And, well, let's start getting used to the idea that reactions happen in forward and reverse. And in this case, 6 of those cyanide anions, will grab onto the iron. So we need to put a 6 here. This is called a ligand. It actually contributes to the bonds. We're going to do more of the specific chemistry later. We can do the electron dot structure here. Okay. So that's how we would draw the electron dot structure for that polyatomic anion. And it's the electrons on carbon that form these bonds. Why is that? Why isn't it the other side? Why isn't it those electrons? What is it about these? Well, carbon is less electronegative than nitrogen. So that's sort of the underlying reason. So these electrons form bonds to that. And I'll show you how you draw that later. And it's really forming a covalent bond. Okay, so some other things here. If we're taking something with positive 2 and something with negative 1, but 6 of them, this whole thing is an ion. 6 negatives and 2 positive, that's going to be a negative 4 charge. So be able to kind of do that math. How many negatives, how many positives, what is the overall charge of the, well now, this is called a complex ion. The transition metal ion has formed a complex with ligands. Okay, nice. So we're getting all the definitions here. So underneath coordination compound, okay, let's see. So coordination number, CN, unfortunately looks like that, is the number of donor atoms bonded to the central atom. Okay. Well, so this one, there are 6 donor atoms. So the coordination number for this complex ion is 6. And we actually know something about this. You can draw this. Do you remember what 3-dimensional shape when you have a central atom with 6 things hanging off of it? You remember what that's called? That's called an octahedral. So this is actually going to be an octahedral complex. So we can actually draw this as, and I don't have models with me here, but octahedral is 4 bonds in the same square plane, and then one above the plane and one below the plane. So 4 in the same plane we have, and let's see, how are we bonding this? We're bonding it through the carbon. So nitrogen and then carbon is forming the bond. Carbon is forming the bond, and then these come out away from the board, and you can shade those in, you can shade those wedges. So these are into the board, these are out of the board. Carbon is forming the bond. I know we keep saying that. Then you have one above and one below. And this is an octahedral complex because it has a coordination number of 6 with, okay. So these all kind of point to the same thing. And sometimes we call this an AX6. And then this whole thing has a, what is it? A -4 or 4 minus. I don't get hung up on which way you do it. Okay, so that's coordination number. What else do we have here? Okay, I'll get to that later. I think I had another example here for you. Cobalt plus 2. I'm not going to put AQ on everything now, or assume that. Well, actually, water is another type of ligand. And oxygen is what does the bonding here. There are no electrons on hydrogen to make the bond, so only oxygen could form the covalent bond. And in this case, it's also octahedral. And it grabs onto it 6 times. You would have to be given that information. Okay, let's do the charge thing. +2 and 0, so this whole thing has a +2 charge. And it has a coordination number of 6. That's fine. It's also going to be octahedral complex cation. So this is a cation. So this is a complex anion. This is a complex cation. And we would kind of draw it the same way. So we'd have cobalt in the middle. This gets kind of weird to draw. Boom, boom, OH2, because it's the oxygen that's doing the bonding. OH2, oxygen doing the bonding, wedge, H2O, OH2. I know that seems strange, but we have to do it that way. You want to show the connectivity. And this whole thing is +2. Okay, wow, I drew that really too big and took up too much space. Okay, so ligands can be monodentate or polydentate. What does that mean? Dentate literally means teeth. It's like how many times does it grab onto the central atom? CN, cyanide, and H2O, those are actually monodentate ligands. The carbon grabs onto it. Fine. Not the nitrogen, not both at the same time. It's just the carbon. With water, water is also a monodentate ligand. How do you know? Well, I guess the easy way to know is, I tell you. Yeah. So, there's a table on the back of this thing that gives you some common monodentate, look at the title, ligands. And then below are some specific bidentate, grabs onto it 2 different places, or polydentate. It's rare that you get more than 2. But anyway, so I kind of tell you what they are, so just know those. You don't have to memorize them, you get to use this on a quiz or a test. Okay, so let's see. Yeah, so there's some that are monodentate. What are some other examples? Okay, well, I guess I can, what is this, number A, B? That's fine, I'm just, you can follow along and make your notes a little bit more organized than I'm doing here. Let me show you some other examples. So those are monodentate. That's typically, there's really only one bidentate ligand or one polydentate ligand we're going to deal with. Let's see, where did I want to go with this? Now, going back to that picture, heme in hemoglobin, oh, this is the abbreviation for hemoglobin, by the way, HB. So the heme, those 4 chunks in hemoglobin, well, that would be polydentate. It's a big ligand. Biological, biochemical ligands tend to be really big because they have to move throughout your body. So that's polydentate. The one we want to spend a little bit of time on is ethylene diamine, and that's bidentate. Why do I say we want to spend some time? Because you're going to use this in the lab. The structure of ethylene diamine is, I think, on the table. Yeah, it's, yeah, okay. Well, here's the dot structure for ethylene diamine. It's CH2, CH2. I'm not going to show those bonds because it gets in the way. And on both sides, so this is a sort of dot structure, are what are called amine groups. Nitrogen is called an amine group, or NH2. Ethyl means 2 carbons. You'll learn about this in organic chemistry. So this is ethylene diamine, and it actually will bond to a transition metal here and here. So this is bidentate. So this will grab onto it twice. It's sort of like one nitrogen grabs on and another bends around and grabs it somewhere else. And let me just show you one example of this. I think it's, so these are, so there's 2 binding sites. Well, how do we draw that? Let me just give you an example. This is one. Iridium, I think I just stole this from your book. Oh, by the way, I'm sorry. EN, this gets a little unwieldy to draw, so we do a cartoon picture of it, and we just show it as this. So there's one of the nitrogens here, one of the nitrogens here, and it's reaching around and grabbing. So we're actually not showing any of the atoms there at all. It's just a cartoon representation because it's easier. So, but sort of, I'll show you how this works. So iridium, 3 ethylene diamines will grab onto it, and this happens, and this is neutral, by the way. This has no charge, and the iridium in this case has a 3+. So the overall complex, this is a complex cavity. You have to be given this. So it's, what's it doing? So it's a bidentate ligand grabbing on 3 times. So it's grabbing on at 6 different places. So the coordination number is still 6, it's not 3. So it's grabbing on, how do we draw this? This gets a little tricky. So it's, why is it not that tricky? It's still this. It's still octahedral. But in this case, what's happening is it's a bidentate, so we want to choose that are 90 degrees apart because we don't want them to go the whole way around. So we would have one ethylene diamine grabbing here. We could have another ethylene diamine grabbing here, and another ethylene diamine grabbing here. So when I say grab, it's grabbing in 2 different places. Again, you wouldn't want these going 180, so choose ones that are 90 degrees apart. There's a couple different ways to draw these. So, whoa, getting messy. So this whole thing would have +3, and this would also be octahedral. And what's at the middle? Well, it's an iridium with a +3 charge. Okay, so monodentate and ethylene diamine bidentate is about all we are going to do. Let's copy down the rest of the definitions. I don't think there's any more. The sample problems we will probably do in class. Okay, fine. Finish copying that down. I want to show you an example that we're going to do in the laboratory, and also want to check on the battery here, see how we're doing. Because quite frankly, if this cashes out on me, that's all right. That gives you the basic definitions. Yes, okay, okay. So, if this suddenly cancels out in the middle of the lecture, of the video, don't worry about it. You have the definition. definitions now. In fact, I think I'll save the last example for a lecture since we're going to do that in the lab. I'm just going to give you an example from the last two definitions here. Ambidentate ligands can grab on either side of the ion. Let me just show you one example. And you can see these on your handout. SCN, thiocyanate, has this structure. And when you would draw it out, it would look like this. It can grab either there or there. So that's ambidentate. And you're told, you're actually given two different ones. Is it N or S? Which side? So just be aware of that definition. And the last one on your notes is what's called the coordination sphere. It's a definition that's really unnecessarily complicated. So when you have a complex ion, you have to have something else that balances it out. So if you have 4 negatives and you're going to have this solid, for example, you would have to have 4 positives out there. So the coordination sphere is what's occupied by just the ion itself. This is not necessarily that complicated. So with the coordination sphere, you just need counter ions. So for something like FeCN6, which has a -4 charge, well, you need some kind of spectator ion to balance that out, like sodium. So we would need like 4 sodium plus 1s to balance that out. That's a 4. For something like, that's an anion. For something like, oh, I don't know, cobalt H2O6 that we did before, that has a +2 charge, well, that would need something negative to balance it out, like chlorine, which has a -1 charge. Okay, that was kind of a messy set of notes, but if you can do the basic definitions, then in class, we'll go over what you're going to do in the lab, and we'll go over those sample problems, and I can just supplement this basics with that. Okay, that's probably long enough for that one, so good work, and we'll see you in class.